Then the return instruction, so it is similar to a jump instruction, but it will pop out the content of the program counter from the stack, and then the program counter will be loaded with that value. So, ret is loading the stack top, it is getting the content from the stack top and putting it into the program counter. So, that the program counter gets back the point to which it should return, and execution continues that way. So, when you are writing a subroutine, so we are doing it like this. So, suppose this is the main program. So, after some time we are calling a subroutine called sublabel. So, this is a call sublabel. So, this is a call to the subroutine. So, this is the subroutine body. So, it should there is a shift. So, this bracket should be in this region. So, that is the subroutine will be there. So, after this sublabel is over, there is a ret instruction. So, ret instruction will take it back to this instruction. So, the instruction just after the call. So, it will take it to this point. But for doing all these operations, for particularly when you are using subroutines in a program, we have to be careful that the stack pointer is initialized to proper value. Otherwise, this return address will be when the processor will try to save the return address, it may inadvertently modify some of the RAM locations which are useful for the program. So, SP, so by default this stack pointer is initialized to 07 after the reset, that is same address as the register 7 of bank 0. Now, with each push operation, first PC is increased. So, when you are first doing the push operation, the program counter will be incremented. So, if you look into this memory, so we remember that there is a register bank 0 which is in the range from 0 to 7, and program counter is also initialized to 7, fine. Sorry, not program counter, the stack pointer is initialized to 7. Now, if you are doing a call, so first this return value has to be saved onto the stack. So, return value will be saved in these two locations, that is location number 8 and location number 9. In these two locations the program counter value will be saved. Now, if your program is using something meaningful, so it is doing something meaningful with these locations, then those contents will be lost. Okay. So, it is better that we initialize this program this stack pointer to some proper value. So, when using subroutines, the stack will be used to store the program counter. So, it is important to initialize the stack pointer. So, in many cases we will use this 2f hex as the stack pointer value. Okay. So, because after that normally we do not have this register banks and all that. So, it is advisable that we put it at around 2f, but in your this is just an advice. So, if you find that your program is using even this location, then you have to find out a suitable chunk of memory that can be used as stack, and you have to initialize the stack pointer that way. And initializing stack pointer is very simple, move sp comma hash 2f hex in this particular case. Okay. So, next we will see an example of this subroutine. So, this suppose we are writing a subroutine square. Okay. So, the square routine what it does is uses it actually squares the number stored in the accumulator, and for that purpose it will use that multiplication instruction and mul AB. So, it will multiply A by B. Now, since B register is being used by the subroutine, so it is advisable that we first save the B register, because the main program from where you are calling this square subroutine may be using this B register also. So, we first save this B register, then we use that B register to get a copy of A, and then we multiply by this mul AB instruction, and at the end the multiplication result is available in the A register. So, it is assumed that since the multiplication result can be contained in 8 bits, okay, the numbers are small enough, so that the result is contained in 8 bit. So, we can ignore the content of B register now. So, we use the pop B instruction, so that this previous value of B is restored, and then it will use the ret instruction to return. So, this is an 8 byte program. Okay. So, this is push B is 1 byte, 2 byte, 3 byte, 4 byte, and this I think some instructions has got 2 bytes. Overall, it is an 8 byte program, and execution requires 11 machine cycles. So, for the details of how these bytes and machine cycles are coming, as we have noted in 8085 also. So, you have to consult the user manual to know the sizes of individual instructions and the number of machine cycles they take. Now, another way of doing this square operation is by this is another program square. So, it increments a, then moves c a comma at the rate a plus p c. So, this will be so this table is located just after the program. So, you see that program counter at this point program counter has got a value which is pointing to the rate instruction. Now, if we are having the value 0, then increment a will have the value 1. So, this is the value 0. So, if the a value was 0, the return value is also 0. If a value was 1, then after increment, so it will become 2. So, the program counter value at this point, suppose at this point the program counter value is say 1000. Okay. Then what happens is that since this rate is a 2 byte instruction, so this table will be stored from location 1000. Sorry, this rate is 1 byte instruction. So, this table will be stored from memory location 1000. So, memory location 1000 will have 1000 will get the value 0, then 1001 will get the value 1, then 1002 will get the value 4. So, that way it will continue fine. Now, suppose the value that we want to square, suppose a equal to say 2. So, we want to get the value 4. Okay. So, when this instruction has been fetched, okay, so program counter value is equal to 1000 because that is the address of this rate instruction. So, with that 1000 we will be adding what? So, we will be adding the value increment a. So, a has become 3. So, it will become 1003. Okay. So, 1003. So, 1001, 2, 3. So, that is wrong, actually this rate instruction is 2 byte. So, rate instruction is 2 byte. So, this is actually 1002. Oh, no, sorry, I am sorry, absolutely sorry. So, this is rate instruction is 1 byte. So, this is going to be this address is going to be 1000. This address is 1000. So, this is 1 byte instruction. So, my table will start at 1001. My table will start at 1001. So, this is 1001, this is 1002, this is 1003 fine. Now, what happens is that a equal to 2. So, a equal to 2. So, increment a will make a equal to 3, then this is a plus p c. So, 1000 plus 3 1003. So, it will access the location 1003 and in 1003 you see we have got the value 4. So, it gets the square value 4. On the other hand, if the value suppose a is equal to 0, in that case after increment a will become equal to 1. Now, it will be 1000 plus 1. So, it will be accessing this location 1001 which will get this 0. So, this way this program also will be computing the same square, but it has got it is faster, the program is faster. You see that this requires 5 machine cycles compared to 11 machine cycles here, because the multiplication instruction takes a number of machine cycles. So, this way we can use this program for getting the multiplication, this squaring done faster. Of course, you can say that this is limited because we are just going up to the value 9. So, 0 to 9 only those squares can be computed by this program, not beyond that. Okay. So, this is another example. So, what it does is that it will compute the square root of value on port 3 and output the value on port 1. So, it will compute the square root. So, how will it do it? So, this is the main program. So, P3 first of all we have to get the value from port 3. So, it says that the value available on port 3. Now, since we want to read the content of port 3 has to be configured as an input port. So, we have to output all 1 onto port 3, that we have seen in the port discussion. So, this initializes port 3 bits to be input, and the next instruction it will read the content of this P3 register into A. Now, we are clearing the bits 7 to 4 by ending with 0x 0f. So, this you see that this 0 will turn off the bits 4 to 7, only 0, 1, 2, 3 they will be there. Now we are calling this square root program. So this square root program, so this will be increment, it will increment a, and then this it will be move c a comma a at the rate p c. So this way it computes the value depending upon the number. So up to 9, so it has got the corresponding digit that should come. So if you are taking that lower order byte, and then after that it is outputting that number to a onto the port P1, and then it is SJMP L1. So SJMP loop. So it will again come here, get the next number, and it will do continue with the program. So correctness of the program you can verify, but the operations are like that. So this is typically just to show you how the subroutines can be written. So this is a way we can write down the subroutine. So why should we use subroutine? So they will allow us to have structured assembly language programs. So we can divide the whole job into a set of subroutines, and that is useful for making the program manageable, and it saves code space because subroutines may be called several times in the program for doing so we do not need to have so much of space for every time. If you want to repeat the same piece of code, then the space requirement of the program will be high. So an example of say delay routine. So this is how is it being done. So this is move a comma 0 a hex. So 0 a hex, a hex is moved onto the a register. Then we are outputting this a register value onto this P0. So this is so this P0 is getting the value. So then actually this program, so this is what this program does is, so if you look into the pattern is a, so a is 10, so it is 1 0 1 0 1 0 1 0. So ideally this program is something like this, that we have got this port P0 from which we have got this LEDs connected. Okay. So we have got this type of LEDs connected, okay, from bit number 0 through bit number 7. And then this LEDs, so they are actually, so you want to blink the alternate LEDs. So that is why that is what this program is doing. So what is it doing? First it is taking the value 0 0 0 a hex into a register and outputting the value to port 0. So alternate LEDs are turned on. Then we have to put a delay there. Okay. So this routine is the will call delay 1. So this will call this delay routine. Then it will complement this a register, and then it will go back to this. So when it complements, then the LEDs which were off previously will be on now, and those which were on previously will be off now. Okay. So it will be doing like this. Now how this delay routine is working? So R0 register is getting the value FF hex, that is 255, and then we are decrementing jump on not 0 R0 here. So R0 will be decremented and it will be looping at this point till R0 becomes 0. For 255 cycles this will happen, and then it will return. So this puts a small delay into this display, so that it is visible to the human eye, and the total delay that is produced, you can find out this move R0 0 FFX, this takes 1 cycle. Then this instruction DJNZ R0 here, so it takes 2 cycles, and that is repeated 255 times, and so the plus the last return that takes 2 cycles. So total altogether it takes 513 cycles. On the other hand, if you want a larger delay, then we can have another delay routine. So here we have got R6 0 FFX, then R7 0 FFX, then DJNZ R7 here. So this is doing it here. Once it is over, so we are doing a DJNZ R6 to back 1. So this is putting 2 delays, okay, through our register pair R6 and R7, and total number of cycles you can compute in a similar fashion. So it is 130818 machine cycles. So once you know the crystal frequency, so you can find out what is the actual delay that is produced by these routines. But so this one has got much higher delay. So next, so this is a long delay example. So we have got this green LED, then SJMP again. So you can just go through this program and see that how this long delay is being used. Then we take another example where we can move a string from code memory to RAM. Okay. So this DPTR hash string, so DPTR will get the get a number from where this string is stored. Okay. So, this is the string. So, this string has got an address. So, when you say hash string, the corresponding address gets loaded in, corresponding address will be coming here, and DPTR will get that address. And R0 is, we are loading how many characters are there. So, this is actually 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 characters. So, there are 16 characters. So, it is 10 hex, and it is terminated with a null character here. So, we are saying that there are 16 characters. Then we clear the A register, then move C A comma @ A plus DPTR. So, DPTR was pointing to this character T. Okay. So, in terms of memory, you can say that if if this is the memory, and suppose from memory location 1000 we have got these characters stored. Okay. So, this is the character T, this is the character H, this is the character I, S. So, it goes like this, and it is ended with a 0. So, this is the string. So, when you execute say this instruction, then DPTR gets the value 1000. So, DPTR becomes equal to 1000. Okay. Now, if you look into say this instruction, what it is saying is it is A plus DPTR. So, A value is 0 at this point. So, A plus DPTR, so it will be accessing this location. So, that character will be moved to A. So, A will get the character T and jump on 0 to stop. So, if you have got this 0, then it will be ending. So, that is over. Otherwise it increments R0. So, it gets the content of A register copied onto the location pointed to by R0. So, R0 setting is R0 is 10 hex. So, it is assumed that this R0 will be pointing to the location where you really want to move the, this is the 10 hex address. So, R0 is pointing to this, meaning that I want to move this string from this location to this location, copy it into the RAM. So, this is move @R0 comma A. So, this T character was there in A register. So, that will come to this location 10. Then increment DPTR. So, DPTR value will be incremented, then increment R0. So, R0 is also incremented. Then SJMP loop 1. So, it will come back here. So, it will again clear SJMP loop 1. So, it will be it should not be here actually. Clear A is clear A, it should come here. So, now this DPTR is now, DPTR value is now 1001. So, with the DPTR, so this again that A will be added. So, that way it will become 1001. So, that it will be pointing to the next location. So, that way it will be getting the next character into the A register, and that character will be moving to the next location pointed to by R0. So, here we have incremented R0. So, R0 is now pointing to the next location. So, the H character will be copied here. So, T character was copied there, H character will be copied here. So, this way it goes on. So, finally, so it will be jump on 0 to stop. When it reaches this 0 character, so it will be jumping to this stop, and here at this point the program is in an infinite loop. So, it is continually SJMP stop. So, it is in an infinite loop at this point. So, we can use this type of program for moving string from code memory to RAM. Next, we will look into another program. So, this is outputting, it is setting this port 0 into input mode, reading the value from port 0 into A register, and then it is putting the value of value that is read in A into the P1 register. So, this basically copying the value coming in P0 port to the P1 port. Okay. So, P0 port the value is copied into P1 port. So, you cannot directly transfer between P0 and P1. So, do it via the A register. Next, we talk about a program that produces a square wave of duty cycle 50%. So, if I have got a square wave, so it has got square wave is like this. Now, this on period to off period. So, this is if I say that okay, this is the start time of a period, then this is the corresponding end time of a period. So, this is the time period T that we have. Now, in this time period, so duty cycle means the on time divided by time period. So, if I say 50% duty cycle, that means for half of the time the signal is high and half of the time signal is low. You can have some other type of wave, like say at this point the signal is high and maybe it comes down, at this time it comes down and then it remains low for this much of time. So, the wave is like this. Say the wave is like this. So, here the duty cycle is much less because the wave is high for much less amount of time, but the time period is same. Okay. So, this way we can have different duty cycles. So, if we are trying to generate a wave of duty cycle 50%, then we can do it like this. So, we want to generate on port 1's bit number 2. So, complement port 1's bit number 2, a call delay. So, a call delay will be produce some delay there, then SJMP back. So, it will be coming back here, or we can do it like this. We can do it explicit set and reset. Okay. So, we can set bit 1.2, then put a delay, then clear 1.2, then again call delay and then SJMP back. So, here the difference is that in the first case it depends whatever be the random value the port has. So, it will be complementing that value. So, we are not very sure about the phase of the signal at the beginning, but in the second case the phase of the signal is initially high and then it goes to low. So, that way the difference between the two cases, otherwise they are same. Another example, suppose we want to make a duty cycle of 66%. Okay. So, if I put the clock be high for 2 times and 2 time units. If the clock is high, then it should be low for 1 time unit. In that case, you can get a duty cycle of 66%, because now this the on time is say, if the total time period is say, sorry, if the total time period is say if the total time period is say 3, and then out of that for 2 time unit, so we are remaining at for 2 time unit we are remaining at high, and for 1 time unit we are going to low. So, the signal is like this, for 2 time unit it is high, then for 1 time unit it is low, 2 time unit is high, 1 time unit is low, then again it is going high for 2 time unit, then it is becoming low. So, that way we can have it. So, this is basically the 2/3 thing. So, this is total is say, if this total is say 2, if this total is say 3, then we can have say up to this much. So, if this is say 3, out of that, so this much is 2 in terms of some time unit. So, we get a duty cycle of 66%. So, how do we do it? We set this port B's port 1's bit number 2, then call the delay routine, then put 2 delays. If there is a 1 call to the delay routine. So, if I assume that it produces a delay of 1 time unit, then I am giving 2 calls. So, I will get 2 delays, then clear that bit. So, it will become low, and then I am putting a delay of 1 unit. Okay. So, this a call delay. So, it will produce the delay of 1 unit for that subroutine, the delay routine, and then it will be SJMP back. So, it will come back to this point. Now, it will again set bit to 1 point, set bit of port 1.2, and accordingly this pattern will be generated. So, that is one way by which we can generate delays and all that, but many times what happens is that for embedded applications you need some precise delay. For example, if you are employing this 8051 microcontroller for designing one traffic light controlling system. So, then the traffic signals are to be on for certain periods of time. So, it is not proportional. So, some fixed amount. So, maybe 1 minute or 2 minute or 30 seconds, something like that. So, but the value should match with the exact clock. Okay. So, for those cases it is not possible to have this accurate delays by means of the software routines that we are looking into so far. So, we have to use some sort of hardwired timers for that purpose. So, 8051 has got built in timers, they can be used either as timer or as counter, and then we can produce some specific delays using those routines, using those hardware. So, 8051 has got two timers counters, a timer counter 0 and timer counter 1, and they can be used as a timer for time delay generation, and in that case the clock source is the internal crystal frequency of 8051. So, it will count time in terms of the internal crystal clock frequency. So, if it is if once we know that crystal frequency, so you can find out like how much value that timer should have. So, we will look into those calculations to produce some exact delays. So, that is one type of utility. Other possibility is you can also use it as an event counter, like you say if there is a conveyor belt onto which items are passing, okay, and you want to make a count like how many items have passed. Okay. So, for that purpose, so every event, so that can generate an external pulse, and that external pulse may be counted by this timer counter module. So, in that case we have to configure that module as a counter, and that pulse instead of coming from internal crystal, so it will come from the this outside pin. So, this is the generic structure, like we have got this timer 0. So, timer 0 it is connected. So, we have got this TL 0 and TH 0. So, this TL 0 and so these are the two registers that will hold the time value, and we can set the initial value for the registers TH 0 and TL 0. Then we can start the timer when 8051 counts up. So, if you start the timer and then so from that point onward, so once you start it, so it will start counting up. The input will come from the internal system clock. So, system clock will give us the input. So, on that basis, so it will be counting it, and when the register content will become 0, so it will set one output bit to denote that a timeout has occurred. So, based on that we can again take some decision to run some other piece of code or produce some external signal for that purpose.